Hello, it's Mr. Teo again. Remember last lesson we talked about the first and second order steady states response and steady states error for first and second order, and then we also proceed to look at the first order plus date time self-regulating and integrating system. So that basically leaves us with the end of chapter 4. Now, today we're going to proceed with chapter 5, and with the beginning of chapter 5, I'm going to introduce to you the PID, which is the proportional, integral, and derivative controller. Without further ado, I will share with you the slides for PID controller. And we shall begin. Sorry, let me share the sound and hide the floating panel before I start.
Chapter 4 in the previous lesson. Now, in Chapter 5, we are going to introduce another block called the controller. The purpose of the controller is to modify the response of the system such that the system is stable and some of the timing specification is met.
Now, so far, for basically, this is a very good overview of the entire module. In the beginning, we start with a chapter 2 by all the sensor, which is the temperature sensor, pressure sensor, flow sensor, and level sensor, which you have went through all this. Then subsequently, we go into the valve, actuator, the flow characteristic, CV computation, and fail-safe mechanism. Then, of course, we move on to chapter 3. That finishes up chapter 2 for the red color one. So then we move on to chapter 3. We talk about signal conditioning. Basically, we look at weak signal. We are supposed to amplify it. And noisy signal, we are supposed to filter it by low-pass filter, high-pass filter, or band-pass filter. Then we talk about the ADC process, whereby we sample and hold, and then we quantize it. So basically, these are the analog to digital conversion. And also, at the very end of chapter 3, we went to digital back to analog conversion, whereby you go to the lookup table, look for the actual analog value, substitute it, create a staircase, and do a filtering to recover the digital signal back to the analog signal. So that basically completed our chapter 3 at this point, right? Then we went into chapter 4. In the beginning of chapter 4, we do the block diagram manipulation, where we try to manipulate a very complex, in fact, in the real life, most plants are very complicated. And then we try to simplify it down into one single block, so that by basically 8 rules, of course, I won't be going through the 8 rules with you right now. And then last week, we just went through for the first and second order system response and error. Of course, prior to that, we also did the first order, second order, the generic equation, the characteristic, etc., etc. Right? Then we also studied the transient response, basically the underdamped case, whereby you have the maximum peak, rise time, peak time, delay time, and of course the settling time, etc., etc. Then last but not least, before coming into chapter 5, we also do a system identification for first order plus date time integrating and first order plus date time self-regulating. So today we are going to dive into PID controller. Both port and stability and Ziegler Nicholas will be the subsequent 2 more lessons.
There are many types of controller available. In this chapter, we are going to introduce to you controller that is made up of P, proportional, I, integral, and D, derivative, elements. A P controller is one that looks at the present condition and deduce and apply a proportional gain control signal based on the present condition. It reduces the steady state error but cannot fully eliminate it. Sometimes gain gets too high, which may lead to oscillation. For I controller, it looks at the past condition using an integrative control signal. I controller is usually able to reduce the steady state's gain to 0. However, the integrative control signal leads to increase in the system order, which may result in oscillation. For D controller, it looks at the future condition using derivative control signal. D controller are usually very responsive to fast changes, hence it is anticipatory in providing damping to the system, making it more stable.
Okay, so the recorded audio pretty much summarized very well the PID controller. Basically, P stands for proportional, I stands for integral, and D stands for derivative. So as you know from the presentation slide here, P is for looking at present, that means looking at the now. For I is looking at the past, that means the history. And then, of course, for the D is looking at the future, right? So you got present, past, and future. So you have got a controller that looks at everything. But of course, in order to control, you have to look at the present situation, what is happening, right? Before you can tell the controller change into this direction and that direction. So that is for the present. Now, you also have collected history information. Like for example, right now I'm at very high. I shouldn't fly higher, because if I fly higher, I will hit the ceiling. So these are what we call the past information, and that is the responsibility of the integrating controller. And then, of course, reacting to the current, what is anticipating ahead. For example, you are traveling in a very fast speed, and suddenly ahead it was turning left and right. So in order to react fast enough, you got to anticipate ahead of time. And that is by looking at the future. And that will be done by the derivative controller. So basically, this is a very comprehensive controller, which look at the present, past, and future, right? But of course, P controller itself can eliminate, as we know what is a steady state error, right? They cannot eliminate totally. But if you set it higher, it will reduce this error, of course, right? But too high may result in oscillation. That's the setback of the P controller that looks at the present. Now for the I controller, fortunately, the steady state error is totally eliminated. So basically, there is no steady state error. When you say you want to use the I controller, basically the main benefit is to reduce or eliminate totally the steady state error. But I controller has one problem, because it has an S in the denominator. Because of this S, it will result the denominator of the entire closed loop transfer function to have additional S, and that may increase the order of the system, which may lead to oscillation. So therefore, this may be the negative point of the I controller, but it looks at the past, right? Now for the D controller, which looks at the future, it basically looks at the derivative. That means the change, whatever change that is happening right now, and it derives a stabilizing control signals to even that out. Let's say, for example, I am moving too much to the right, it will just push the control to the left. So that's why it's trying to normalize it. So that's basically a PID controller for you.
P, I and D element can be used based on need and requirement, and a number of combination can be made out of it. Possible combinations listed are P, I, D, PI, PD, ID and PID. Whichever element P, I or D is used, GC, S, will contain the respective controller parameters. These parameters, like Ki over S or KDS, are in S domain. If a time domain expression is needed, a Laplace inverse have to be performed.
Now, PID is just the general name, PID. But of course, it's like going for a buffet. This is all that you have on the table. You can just pick and choose any one of them, or the combination of two or more, right? So the possible combination that I have tried to run out is basically you can use a P alone, you can use an I alone, you can use a D alone, then you can have PI combined, or you can have PD combined, or you can ID combine, right? Or last but not least, the more complicated one will be the PID, or in combination. But of course, you don't just choose the controller because the name PID looks nice or ID looks nice, right? Basically, it must fit the purpose, right? Fitting the purpose means that it must be able to meet the specification that we intended it for. Now, of course, if I can design a P controller that meet the entire technical specification, I would rather choose the P controller over a PID controller which also may be able to meet the same specification. Why? Because a P controller will be more in terms of architecture and in terms of simplicity, it is much simpler compared to a PID controller, right? And as we know, for any engineering design, simplicity is beauty. So therefore, if you can come out a solution with just a P controller, by all means, right? But of course, if cannot, then you move to the next level, whether it's PI, PD, or ID, right? Controller. So of course, then if still cannot, you just move all the way to the PID controller. And that's basically the choice. But of course, if you choose just the P controller, that means only the KP path exists. Then the other two paths will be eliminated. So for the equation wise, you don't have to include Ki over S and you don't have to include Kd over S. Just G of Cs equals to Kp. That's what we mean. So if you choose a PI controller, on the other hand, you have to include this path, Kp, and you have to include this path, Ki over S. But Kd, no need, right? So therefore, in your GC expression, it will be GCS equals to Kp plus Ki over S. Of course, there is a PI controller, Kd is not, Kds is not there. So on and so forth, right? Now, of course, in the full PID controller, the controller expression will be Kp, which is the proportional P controller, Ki, which is the integral controller that look at the past, and Kd is the derivative controller that look at the future. So this is the full expression for PID, right? PID in the S domain, in the Laplace domain. Now, if you want the time domain equivalent, then you got to do an inverse Laplace, right? Inverse Laplace, and then of course, inverse Laplace, after that you can multiply by your error function in the time, and that gives you your basically G of t at output here, right?
Let's now take a closer look at the P controller equation. GC will contain Kp only because the I and D controller is not used. Using Rule 7 for negative feedback in block diagram manipulation, the C, S, over R, S transfer function can be simplified to Kpgp over 1 plus Kpgp. Notice for P controller as Kp increases, the peak time, settling time and steady state's error decreases, whereas the maximum peak increases.
Now, this is to roughly, we start off with a P controller. So basically on the control portion, we just choose P, Kp, right? You notice that the Ki over S and Kds is not there because we are using only the P controller, right? So of course, the plant will remain as Gp. Now, if you look at this block diagram, we can pretty much very easily simplify it using Rule 7 of block diagram manipulation. So it's G is Kp, Gp. And then over 1 plus G, again, Kpgp. Of course, H is 1, so you don't have to write it. Actually, it's multiplied by 1. Right? So this will be your C of S over R of S. That means the output over input using the Rule 7. Right? And we observe that for a P controller, as you increase the Kp, that will be the effect. The peak, the TP, the peak time will actually shorten. The MP will increase, the maximum peak will go up, the settling time will go down, and the steady state error will decrease. That's the observation for most of the P controller, or in fact, that is the consistent behavior of the P controller.
Pictorially, if we look at the underdamp response, by increasing Kp, you can see that MP increases whereas TP, TS and ESS decreases.
So pictorially, when we say we increase Kp, each of these functions change in certain sense. Like for example, if I increase Kp, MP increase means that this peak will go higher. And then of course your TP reduce means that your peak will shift to the left. That means your timing to reach the peak is very short. And then TS also reduce, so it means it settle down faster, maybe settle down in the earlier stage. And of course, the ESS reduce, right? So that means the steady state error actually is getting smaller, right? So that's what we mean when we say all these things.
Let's now take a closer look at the PI controller equation. GC will only contain Kp and Ki over S because D controller is not used. Using Rule 7 for negative feedback in block diagram manipulation, the C, S over R, S. Transfer function can be simplified to bracket KPS plus KI multiplied by GP over S plus bracket K. PS plus KI multiplied by GP. Notice for PI controller as KI increases, the rise time decreases, whereas the maximum peak settling time increases. Notice also that the steady state error can be totally eliminated.
So this second one, we are trying to look at the combination of P and I. So therefore, if you look at the GC controller, the controller transfer function is Kp plus Ki over S. There's no Kd involved. So again, using rule 7 of block diagram manipulation, you have G, which is this guy, G. But of course, I make it into a common denominator. So I put a S below and put a S to the side. So it's Kps plus Ki over S, right? So this is G. Of course, you multiply by GP. So this entire thing is G over 1 plus G. H is 1. H is times 1. So after that, you simplify this, you will get this kind of a response. And then, of course, through empirical study and testing, it has been known that Ki, by increasing it, you will reduce your rise time, you will increase your maximum peak, and you will increase your settling time. And of course, it will. The best thing is it will eliminate your steady states totally, steady states error totally.
For PD controller equation, GC will only contain Kp and KDS because I controller is not used. Using rule 7 for negative feedback in block diagram manipulation, the C, S, over R, S, transfer function can be simplified to bracket KDS plus Kp multiplied by GP over 1 plus bracket K. DS plus Kp multiplied by GP. Notice for PD controller as KD increases, the rise time, settling time and maximum peak decreases, whereas the steady state error only change in a small magnitude.
So just now we talk about P and then we talk about PI. Now we repeat it for PD. So PD, you just include the Kp and KDS, right? Ki over S no longer used, right? So therefore, the GC transfer function is this. So your new gain right now is GC, which is Kp plus KDS multiplied by GP. So this is your new G. And then also over 1 plus G, H is 1 again, multiplied by 1, so there's no difference. So this will be your closed loop transfer function for your plant with PD controller, right? Now, notice also that through empirical study and measurement, it has found that increasing KD will result in a reduce in the T rise, reduce in the maximum peak, and reduce in the settling time, right? And of course, it has a very little change to your steady state error, right? So there's not much change. If you wish to minimize the steady state error, you don't use a KD. I mean a D controller, right?
For PID controller equation, GC will contain all Kp plus Ki over S and KDS. Using rule 7 for negative feedback in block diagram manipulation, the C, S, over R, S, transfer function can be simplified to bracket Kp plus Ki over S plus KDS multiplied by GP over 1 plus bracket Kp plus Ki over S plus KDS multiplied by GP. Notice for PID controller the effect will be the combine effect for Kp, Ki and Kd.
Okay, so of course the most complicated controller that you can have for PID will be, of course, all the component included, meaning that the P here, you include the Ki over S and a KD. So every items you include, and of course, by including everything, then your new G will be more complicated. And basically, you can write your G over 1 plus GH here using rule 7 of block diagram manipulation. Okay, so of course, the characteristic of Kp will remains the same by itself. If you just change the Kp, you will change according to what we talk about in the P controller. If you change the I, it's the same as what we talk about in the I controller and KD as well. So therefore, we don't need to repeat it in the PID controller.
Now let's look at a first order system. 0.2 over S plus 0.1 with P controller and unity feedback. Again, using Rule 7 for negative feedback in block diagram manipulation. C S over R S can be simplified to 0.2 kp over S plus 0.1 plus 0.2 kp. If we let kp equals to 1 and 10 and substitute to the C S over R S first order equation, we will realize that the settling for kp equal 1 and kp equals 10 will be 16.66 seconds and 2.4 seconds respectively. Here, it clearly shows a reduction in settling time when kp is increased from 1 to 10.
So this is example 1 that we are trying to investigate the effect of kp on the plant that is given by this expression 0.2 over s plus 0.1, right? So of course, if you want the closed loop transfer function of this expression, you got to do your g over 1 plus gh, which is rule 7 of block diagram manipulation. And after doing it, you will be able to simplify it into c of s over r of s is equals to 0.2 kp over s plus 0.1 plus 0.2 kp, right? So this is the finalized transfer function for c of s over r of s. Now, if we choose kp equals to 1, then you just substitute 1 here, substitute 1 here. Then your new expression after substituting the kp equals to 1, you get 0.2 on top, and bottom you get 0.3. So it's actually a first order equation, right? First order equation. Now, first order equation, in order to compare, we got to make sure that this item here is 1. So we divide the top and bottom by 0.3. So if you divide top by 0.3, the bottom by 0.3, and this one by 0.3, you get 1. Then you got 0.67 over 0.33, 3.33 second, 3.33 s, not second, plus 1. So basically, this is your k, this is your tau, and plus tau s plus 1. So basically, from here, you can realize that the steady state gain, which is k, is 0.67. And then, of course, your tau is 3.33 second. And of course, your settling time will be 5 tau. 5 times 3.33 give you 16.66 second. So that is for kp equals to 1. Now, if you substitute kp equals to 10, then the expression looks very different. Instead of 0.2 over s plus 0.3, now you have 2 over s plus 2.1, right? 2 over s plus 2.1. Now again, in order to compare with the first order system, you got to normalize this guy to be 1. So you divide by 2.1 throughout for all the items. So on top, if you divide by 2.1, is 0.95, and bottom is 0.48, right? Plus 0.48s plus 1. So basically from here, your steady state error actually went up to from 0.67 to 0.95, right? And of course, your tau also increases, also reduces from 3.33 second to 0.48 second. And of course, your settling time, which is 5 tau, has reduced drastically from 16.66 second to 2.4 seconds. So you can see that by increasing the kp, the gain, by 10 times, you actually reduce the settling time by so much, many folds. And also you make the steady state response much higher. And of course, by being the fact that we know that the input is settling at 1, so therefore the steady state error of this second case will be much lower than the first case, right?
As can be seen from the simulation for this example, using only P controller, when Kp increased from 0.5 to 10, the rise time and steady state error reduces. This is consistent with what is stated in the previous page's explanation on the effect of increasing Kp. Note that the maximum peak and peak time cannot be commented, as Kp is not increased huge enough to cause peaking.
So this is a plant characteristic by itself. And then, of course, this is including the P controller. So if you set your first time your P controller to be 0.5, then you move it to 1, and you move it to 10, you can realize that the response get faster as your Kp get higher. And also the steady state error here has been reducing, right? So therefore, it is consistent with our finding in the previous page, right? Whereby we say that, hey, the settling time is much faster because 5 tau, now right now the tau is so small as compared to the tau here, right? Tau, remember, is reached 63%, And then of course this guy reached the 63%, probably is here, so it's much longer, right, compared to this guy. So therefore, with that, that would be the P controller itself.
Now let's study the effect of P controller on second order system instead. Here the second order system used is 1 over S bracket S plus 2. Again using rule 7 for negative feedback in block diagram manipulation. C, S, over R, S, can be calculated to be Kp over S square plus 2S plus Kp.
So this is right now, we try the Kp, just now we tried on a first order system, but right now we use a second order system, 1 over S plus 2, right? This is the second order because if you multiply this in, the highest power will be squared, right? So S squared, so therefore this is a second order system. So if you do this, the closed loop transfer function using rule 7 again, your G is here, and then of course your H is 1, so it's G over 1 plus GH will result you into having this expression Kp over S squared plus 2S plus Kp, right? So this is your closed loop transfer function using rule 7 of block diagram manipulation.
Now if we substitute Kp equals 0.5, 1 and 3 to the expression for Cs over Rs, we will see damping ratio equals to 1.4141 and 0.58 respectively. Clearly increasing Kp resulted the system to move from overdamp to critically damp and finally to underdamp.
So basically, if I were to substitute the Kp of 0.5 or Kp of 1 and Kp of 3 into the previous expression here, then
now if we table,
then you will get basically 3 different expressions for the 3 case, right? 3 different expressions for the 3 case. Now, of course, in order for us to analyze this guy, we got to equate it to your generic equation, which is S squared plus 2 zeta omega n S plus omega n squared. This is your generic equation. This is your closed loop transfer function. After equating it, we will be able to find what is omega n and zeta, right? So similarly for the 3 case. So by looking at this, we can see that this is an overdamp case because the zeta is actually 1.414, much greater than 1. So this is called an overdamp case. Now, for the second case, we realize that the zeta is just nice at 1. So this is what we call a critically damped case. And then, of course, for the third case, when the Kp is 3, we found that the zeta is actually 0.58. So this become an underdamped case. So by shifting the Kp from merely from 0.5 to 3, you can see that the whole entire transfer function, the closed loop, move from overdamp to critically damped to underdamped. So of course, when underdamped happen, there's slight peaking here occurring, but of course the rise time is much faster.
Table below summarizes the effect of increasing Kp to the rise time, overshoot, settling time and steady state error. Increasing Kp reduces rise time, settling time and steady state error. On the other hand, it increases the maximum peak or the overshoot.
Also, this is the net effect. By changing your Kp from 0.5 to 1 to 3, your damping ratio changes. Also, the rise times drop, overshoot increase, settling time drop, and then steady state error drop. So that's the observation that is being found.
Now instead of using the P controller, we use PI controller. The net effect of increasing Ki while keeping Kp constant at 5. Increasing Ki causes rise time to decrease, whereas it causes settling time and maximum peak to increase. Also to note is that the steady state error is totally eliminated when a controller is being introduced.
So for this case, we changed the controller to PI controller. And then, of course, right now, still using the same second order transfer function, you can rewrite your closed loop transfer function using rule 7, which is G over 1 plus GH. We will simplify it into this fashion, right? So take note that as the Ki increase from 1 to 3 to 5, so basically 1, 3, 5, you realize that the rise time actually decrease, the overshoot increase. As you increase Ki, the settling time increase, and of course the steady state error is eliminated. As we already know that this kind of steady state error equals to 0 for I controller.
If we, instead of using the PI controller, we use PD controller, we can see the net effect of increasing KD while keeping KP constant at 5. Increasing KD causes rise time, settling time and maximum peak to decrease. The steady-state error, however, does not experience much change when increasing the value for KD.
So now, right now, instead of using PI controller, now we're trying PD controller. Again, using Rule 7 or block diagram manipulation, you can simplify your C of S over R S as follow, as this expression. So if we try to increase your KD from 1 to 3 to 5, 1, 3, 5, then that's how your response will move. It will basically, the rise time will basically be reduced, the overshoot will be reduced, settling time will be reduced, but the steady state error, very small change.
This page gives the summary of the effect of the PI and D on the second order system.
So having run through the PID, PI, PD controller and telling you the response, what happens, the effect of KP, KI, and KD increasing. So this is a summary table to show you that. So basically, next time you design a P controller or I controller, D controller, you know by increasing this, how does it affect the rise time, overshoot, settling time, and steady state error. So you can refer to this table quite effectively to point out, hey, what direction should I move in, right?
Please watch the video to understand how PID can be applied to drone level control.
Illustrate this with an example. Imagine you are standing on the goal line of a soccer field, and you want to walk to the half field line 50 meters away. In this case, you are the plant. The actuating signal is the speed and the direction that you walk, and your current location on the field is the output variable, or 0 meters to start, and then 50 meters is the command. Therefore, at the beginning, your position error is 50 meters, or 50 minus 0. You still have a ways to go. Your brain, being the controller, tells your legs how fast to walk. And one way your brain can do this is to use the error at the present moment to decide your walking speed. Here I've set our controller to the value of 0.1. This means that if we take the error in our system and multiply it by 0.1, we'll get our walking speed. So if our error is 50 meters like it is at the beginning, then we'll start off walking at 5 meters per second. With a proportional controller like this, we start reducing the error quickly since we're far away, and then gradually slow down as we get closer and closer to our goal. In this way, we would eventually and asymptotically reach the half field line, at which time the error would be 0, and our proportional controller would multiply that by 0.1, which would generate a walking speed of 0, stopping us right where we want to be. If we wanted to adjust the amount of time it took us to get to the goal, we could increase or decrease the multiplier term. Regardless of the gain value chosen, this type of controller will eventually cause us to stop right on the goal line. So this proportional controller seems great. I mean, just multiplying the present error by a number seems to work. Well, let's try it again on a different system and see if it performs the same way. In this second example, you want to design an altitude controller for a quadcopter drone. The drone has 4 propellers, and when they all spin up together, they produce a force that lifts the drone up into the air. This is similar to our walking example in that we're trying to get to a specific location, but this time we want to get our system to hover at an altitude of 50 meters. Our plant is the drone, and the output of this system is altitude. Now, the input of the system is not walking speed, but propeller speed. And all in all, it seems like a pretty similar problem. So how well does a proportional controller work in this case? Well, when the drone is on the ground, there's an error of 50 meters, which would generate a large propeller speed, causing the drone to lift off and start to rise, reducing the error. So far, so good. But let's imagine the drone was able to rise all the way to 50 meters. What would happen now? Well, the error would drop to 0 since the command and the output are both 50 meters. This would then shut off the propellers, lift would stop, and the drone would fall back to Earth. Now, when that happens, the propeller speed would start to increase again as the error grew. There is a certain propeller speed where the lifting force is exactly equal to the weight of the drone, and at that speed, the drone will hover. So where would our proportional controller hover this drone? Well, that depends on the controller gain. Now let's assume for the moment that the propellers need to spin at 100 RPM in order for the drone to hover. If our proportional gain was 2, then the drone would hover right at ground level, since an error of 50 times 2 is 100 RPM. However, if we increased the gain to 5, the drone would rise at first, but then stop at 30 meters, since the error at that point would be 20 meters, and 20 times 5 is 100 RPM. A gain of 10 would produce an error of 10 meters, and a gain of 100 would produce an error of 1 meter. And no matter how high we increase the gain, the error won't go away. It'll just get smaller and smaller with this system and a proportional controller. So we can see that a simple proportional controller doesn't work in every situation. It works with our walking example, but for our drone it created this constant error. This error is also called steady state error. So how can we tweak our controller to get rid of this steady state error? We can do that by letting our controller use past information, or specifically adding an integrator path in our controller that's added alongside the proportional path. An integrator sums up the input signal over time, keeping a running total. Therefore, it has this memory of what has happened before. Basically, it's keeping track of the past. Now, if the drone gets to steady state below the desired altitude, the error term is non-zero. And when a non-zero value is integrated, the output will increase. Now, as long as there's error in our system, the integral output will continue to change. And this increased value from the integrator path will increase the speed of the propellers, and the drone will continue to rise. These two paths, the proportional and the integral path, work with each other to drive the error down to 0. And with this controller, when the drone is hovering at the desired altitude of 50 meters, the proportional path is doing nothing since the error is 0. But the integral path has been summing and subtracting values until it came to rest at 100 RPM. Remember, this is what we said was needed for the drone to hover. And that output from our integrator will not change, since the input to the integrator at this point is 0. Alright, this proportional integral controller is it. This is what we want, right? Something that understands the present and has memory of the past. Well, looking at the past and present error will get us to our goal in this situation. However, the path the drone takes to get there might not be ideal. Imagine this situation. Right before we get to 50 meters, there's an interesting situation that can occur. The proportional path is basically 0 since at this point the error is so small. But depending on how the drone got to this height, the integrator may have summed to a value over 100 RPM. This would cause the drone to keep rising, which is what we want since we're below the 50 meters. However, to remove that excess propeller speed, the drone will have to go higher than our goal to create a negative error. This negative error, when summed, lowers the output of the integrator and slows the propellers down. This overshooting of the goal might not be desired. Luckily, there is a simple way around this problem, and that is by adding a path to our controller that can predict the future and respond to how fast we're closing in on our goal. And we do that with a derivative. A derivative produces a measure of the rate of change of the error. That is, how fast the error is growing or shrinking. For example, if our drone is rising quickly and fast approaching our goal, this means that the error is quickly decreasing. That decreasing error has a negative rate of change, which will produce a negative value through our derivative path. That negative value will be added to our controller's output, therefore lowering the propeller speed. Basically, our controller is using changing error to determine that we are closing in on our goal way too fast, and then prematurely slowing down the propeller speed, preventing the drone from overshooting. And just like that, we've created a PID controller, proportional, integral, derivative. This is a versatile controller that uses the present error, the past error, and a prediction of the future error to calculate the appropriate actuator commands. These three branches each contribute some amount to the overall output of the controller, and as the designer, you get to decide how to weigh each contribution. You do this by adjusting the gain term in each branch. This is called tuning the controller. Now, if your controller contains all three branches, it's called a PID controller. Now, if the gain of one or more branch is set to 0, taking it out of the equation, then we typically refer to that controller with the letters of the remaining paths. For example, a PI or a P controller. PID is just one form of a feedback controller, but they're pretty easy to understand and implement. They are the simplest controller you can have that uses the past, present, and future error, and it's these primary features that are needed to satisfy most control problems. Not all, but a lot of them. That's why PID is the most prevalent form of feedback control for a wide range of real physical applications. Now, there's a lot more to learn on this topic, and if you stick with this series, we're going to explore PID controllers in more detail. Now that we have a general understanding of what PID control is, we'll move on to how we implement one, how we tune it to do what we want, and we'll watch it in action on some real hardware. So if you don't want to miss these future Tech Talk videos, don't forget to subscribe to this channel. Also, if you want to check out my channel, Control System Lectures, I cover more control theory topics there as well. Thanks for watching, and I'll see you next time.
So this is a pretty interesting controller, PID controller for drone, right?
Please proceed to watch
With that, we
tutorial
will start to
13.
discuss on tutorial 13. So basically, we have 3 questions for tutorial 13. I will go straight into the question and whiteboards, and we will just discuss based on that. So for question 1 and 2, pretty much is a theory question. So we'll go straight to the question and answer. And then for question 4, there's some calculation, then I will use the whiteboard. Okay. Let me right now look at the sharing of the question, right? Sharing of the question. So okay, let me look at other. Okay, the question is over here. Okay, so for question 1, they ask you to write the general PID equation in the time domain as well as the S domain, right? In question 2, they ask you to explain what you mean by P controller, what do you mean by I controller, and what do you mean by D controller response. So I'll show you these 2 questions progressively by sharing with you the answer, right? Now for question part 1, this will be your time domain expression. You can actually also see it in your lecture notes. Just now, in the beginning when I start presenting it, this will be your time domain expression. And of course, the S domain expression is Kp plus Ki over S plus Kd multiply by your error function. And that is both your time domain and your S domain function. Now, as for PID control system response, you can also leave all these things from the text or from the detailed lecture notes. And basically, it goes this way. P controller, the P action is actually a proportional instantaneous error. There will also be a steady state error if there is any disturbance in the system. But we, by and large, understand that the P controller looks at the present, and it by increasing the P controller, you can reduce the steady state error. But too high a P controller will result in oscillation. Now, integration controller, basically, if you go according to this text, is controller output is a signal which keep adding. That means integrating all the values of the error over time, thus allowing to compensate offset due to the load changes. And we also understand that the I controller looks at the past, or it takes the past information and then decide on what's the next course of action, right? And I controller, when you insert the I controller in, it basically eliminates all your steady state errors, so there is no steady state error. But of course, the I controller, because there is a Ki over S, this S will result your denominator expression of your entire transfer function to have additional S, meaning that it will increase your order. And because of this increasing of order, it will result in oscillation. Now, for the D controller, if you read this text, it says that it's controller look at the rate of change of error and pulls the action back if it sees this rate of change and will overshoot and set it nearer to the future. So basically, it's an action that looks at the future future anticipation. If it's turning right, you will move more to the left to counter the action. And of course, with this D controller, we expect the system to be more stable because it's KDS. There is no 1/S term. And then, of course, it look at the future and anticipation. So that is for question 1 and 2. Let me right now go to the next question. Next question will be question 4, P controller, second order. So let's go to the question 4 right now. Question 4 and read the question, right? So question 4. Okay, this is also a short question, but the mathematics might not be short. So for the system shown, so this is a system. So you have the plant expression as 1/s² plus 4s plus 1. And you have the controller they use is a P controller because it's just K itself, right? So determine the value of K at which the system starts to oscillate. So they ask you, what is the value of K where the system starts to oscillate? So you can imagine that if you start increasing the value of this P controller, at some point it will start to oscillate as mentioned in the P controller. So this is a realistic question. It's not a question that is fake up. So there is a possibility that a certain value of K, when you increase too high, it will cause the whole system to oscillate. So comment on the effect of K on the damping ratio and the frequency, natural frequency. Damping ratio is the zeta. Natural frequency is your omega n. So basically, that's the few thing. Now let's go to the whiteboard, and solve this question. Okay, I hope you can see the whiteboard. Let me shift this thing a little bit and get the pen out. Okay, now where's my pen? Okay, my pen is over here. So let's look at the expression again. You have 1/s². Okay, so the plant is G is actually G of S is actually 1/s² plus 4s plus 1, right? You hold on for a while I go and answer the. Okay, it doesn't matter. So this is your gain, and then of course you have your K there. So if you were to try to simplify this expression using G/1 plus GH, then you would have the output Y of S over input U of S, and you will get G, which is 1/s² plus 4s plus 1 over 1 plus 1/s² plus 4s plus 1. Maybe you excuse me for a while I go and answer the door. Okay, sorry for the delay. So basically, you have that, right? So basically, this is G/1 plus GH. H is 1, right? H is 1. So because it's a unit feedback. So with this expression, you try to solve it, you get 1/s² plus 4s plus 1 over this 1 here, you can change it to s² plus 4s plus 1 over itself, right? Over itself. So this is actually equivalent to 1, right? Then of course plus your 1 over the same expression, s² plus 4s plus 1. So if you try to combine this, you get 1/s² plus 4s plus 1 over the top. You can combine them together is s² plus 4s plus 1, and plus 1, right? So it's plus 2 divided by s squared plus 4s plus 1. So the top and the bottom is the same, so you cancel it out. So what you have is 1 over s squared plus 4s plus 2. So this is your expression, closed loop transfer function for your entire expression, right? So the question asks you, determine the k value such that the system will oscillate. Now, in order for the system to oscillate, we need to know that the roots of the equation must be complex, right? So this is your roots of your, that means the roots of this denominator here, right? How to check the roots of the denominator? So basically, if you have roots of denominator, you want to find the solution. It's basically using S1 or S2, which is roots of this equation, will be equals to minus b plus minus square root of b squared minus by 4ac, right, over 2a. This is your secondary school mathematics for solving the roots of a quadratic equation, right? So now b is 4, right? So minus 4. So minus 4, it will give you minus 4 over here, plus by minus square root of 4 squared, right? b again, 4 squared, minus by 4a, 4 times a. What is a? A is 1, and c is 2, right? And also you divide it by 2a, 2 times 1, right? So if you try to solve this, you get minus 4 plus minus square root of 16. 4 squared is 16, minus by 8. Did I miss out anything? Oh, there is a kp. Let me see. There's a kp. Sorry, there's a k here because this is just g. There is another gc which is actually k, right? So you got to put a k here and put a k here, right? So this guy also is a k here, right? And also a k here. So this is actually 1 plus k, not 2. So this one, it should be 1 plus k, right? So your c itself is actually not 2, but let me erase this properly. Your c here is actually 1 plus k, right? 1 plus k here. And similarly for this case here, you have a c here. It's not 2, but rather 1 plus k, right? 4ac, right? So it's 1 plus k. So you have 16 minus by 4 times 1 is 4. Minus by 4 times k is minus k, right? Okay, over 2. Right? So if 16 minus by 4, you get 12, right? So it's actually what you have here is 4 plus minus square root of 12 minus by k divided by 2, right? Now 4 divided by 2, you get 2 minus 2 plus minus. Okay, you can just divide this side first and then you put to this side, right? So it's a square root of 12 minus k divided by square root of 4, right? Square root of 4 is 2. So 12 divided by 4 is 4. 12 is 3, right? So basically you have, sorry, this should be 4k here. This should be 4 times k is 4k here. So it's 4k here. It should be 4k over here, minus by 4k. Right? So you can rewrite it as minus 2 plus minus square root of 12 divided by 4 minus 4 over 4k. Okay, so we rewrite it here, over here. We get equals to minus 2 plus minus square root of 3 minus k. Right? Now, plus minus here. Now, in order for this solution to become complex, you remember that for underdamped case, under them, remember, under them case, it is the start of oscillation, right? Start of oscillation. Why do I say so? Because in your under them you have picking and trolling. So this is your start of oscillation. If you move much more gain, then you will start to oscillate. So this is the beginning of oscillation. So you remember your under them, the root of the denominator has a J term, right? Has a J term. That means it's a complex conjugate term, right? Complex conjugate with plus minus J term. So likewise, if I want to make this into a J term, that means this guy, the square root must be less than 1. So meaning that the situation of this less than 1 is when k is greater than 3, right? When k is more than 3, this whole term becomes negative. Now, when you have a negative, what happens? Let's assume k equals to 4. Now, if k equals to 4, what happens? K equals to 4, then your roots will be 2 plus minus 3 minus by 4, right? Now, what is 3 minus by 4? It's minus 1. So it's actually equals to 2 square root of minus 1. Now, square root of minus 1 we know is j. So it's 2 plus minus j. So now you have an imaginary term, or because of this root 1. Of course, you can have equals to 5, then you will be plus minus j2. So on and so forth. So basically, the correct range of k, when k is bigger than 3, it will result in oscillation. And that's the part 1 of, that is, we are answering first part of the, basically the question. Right? Now, let's look at which part we have not answered. Now, he said comment on the damping ratio and natural. So if we go back to your whiteboard right now, so we understand that k has to be greater than 3 for it to start to oscillate. Now, also, this is your closed loop response, right? This is your closed loop response. And by comparing it to your generic equation, remember your generic equation is the denominator will be s squared plus 2 zeta omega ns plus omega n squared, right? So if you want to find the relationship with natural frequency, the non-S term, that means omega n squared. If you try to equate it to 1 plus k, then omega n will be square root of 1 plus k. So what is the effect of k on natural frequency? Increasing k will basically resulted the omega n to increase at the square root rate. So that's the effect of k. Right? Now, what about the other one? The damping ratio. So we can also equate 2 zeta omega ns to basically 4s, right? 4s. And then if you divide this, zeta will be equal to s cancel. So you have 2 over omega n, or equals to 2 over square root of 1 plus k. So increasing of k will result in the reducing of zeta. Right? Because k increase is at the denominator, then the damping ratio will reduce. So that is the answer for question 4, right? One of them is k greater than 3 result in oscillation. So this is Q4 of tutorial, question 4 of tutorial. Right? So question 4 of tutorial, this is, one of them is k greater than 3 result in oscillation. The other one, the effect of k on natural frequency, and the effect of k on zeta, which is damping ratio. Okay, with that, I have completed today's lesson. I wish you all the best. Thank you. Bye-bye.